In this video, you're going to be learning about how to identify and graph properties of rational functions. But first, let's talk about what a rational function even is. A rational function is a function that can be written as some type of function equals p of x divided by q of x, where p of x and q of x are polynomial functions. Meaning, basically, what it's saying is that as long as you have a polynomial function on top and a polynomial function on bottom as a fraction, then it would become a rational function. The domain of that function is going to be all real numbers except for where the denominator, that would be the denominator, where the denominator, I can't even spell, where the denominator is equal to 0. Because if you have a 0 in the denominator, you would have something that is undefined. So for example, I have two examples for you that are both rational functions. Now you may say, wait, that number is not a rational that function is not rational because you have a number in the numerator. But if you think of it as x to the 0 power, that is a polynomial function, which would actually give you 1. And so 1 divided by a function will give you a rational function. Now, in this case, when we talked about the denominator can equal to 0, so if you notice that this denominator, if you were to plug in 2, or if you were to plug in a -2 into this x, you would actually get 0 in the denominator, which is undefined. And what happens there is you actually get something which is called a vertical asymptote. It is an imaginary line on your graph that the graph cannot cross at all. That happens at 2 and it happens at -2. Again, this is not on the graph if you were to graph this in a graphing calculator, but it is an imaginary line to where the graph cannot cross over at all because you cannot get 2 or -2 to work because you would get a 0 in the denominator. Same thing applies in the second one. If I was to actually plug in a -1 here, then I would actually get a 0 in the denominator again. And so again, there's an imaginary line that is the vertical asymptote at -1 that this graph cannot cross. Now, talking about vertical asymptotes is actually a much broader term called points of discontinuity. And there's two ways you can have that. You can have a hole, which is actually called a removable discontinuity. That's one way to describe it. And then you could have something that is an actual vertical asymptote. A hole happens to where you can have something that possibly gets factored out and reduced. Meaning, if I was to take this function and I notice the top, you can factor out an x on the top. You can pull it out. And on bottom, you have x plus 3. And something that happens is you have something that's in the numerator and the denominator that's the same. And so therefore, what is left is just y equals x, which is exactly what this line is. This line is the graph y equals x. If you were to graph this original problem in your graphing calculator, it looks like a line. But right there, something happens. Now, you cannot see it on the graphing calculator, but if you were to toggle or trace down that line, when you hit -3, you actually will not get an answer for y. Because if you plug -3 into your original problem, you actually would get a 0 divided by 0. Again, 0 in the denominator is not allowed, and so that is why you have a hole there. It's not possible. But because that hole or that undefined part, because it actually cancels out, leaving you with something that you can actually graph. That is why this is called a hole and not an asymptote, is because this graph is completely continuous except for where you were able to reduce that fraction. In the second one, you cannot reduce x plus 4 and x minus 1. There is nothing that you can multiply by that will cancel anything. And so when you get your denominator, what's left over, x minus 1, and you were to set it equal to 0, that means at 1, you actually have a vertical asymptote. That graph cannot cross it at all. This is considered a removable discontinuity because you are able to remove the denominator. leaving you with something that can be graphed that has a nice domain. So let's actually practice this. We want to find any points of discontinuity and determine what they are, meaning they could either be a whole or they can be a vertical asymptote. So on this first one, let's see if there's anything that can be reduced. I am going to factor the numerator out, and on bottom I'll get x plus 2. If I factor the numerator, it would factor into x plus 2 and x plus 3. Now, if you look at things to see if there's anything that cancels, there's an x plus 2 on top and there's an x plus 2 on bottom, leaving you y equals just x plus 3. So that is what your final graph will look like. However, because you originally had something in the denominator, you're going to set it equal to 0, and when you solve, you'll get x equals negative 2. That is called a whole, or what we just discussed is a removable discontinuity. Removable because we actually removed it from the equation, leaving you something that you can plug negative 2 into. You would get a 1 if you did. But again, when you graphed it, you would have a whole because in the original problem, there was an x plus 2. But since we were able to, again, remove that discontinuity, that is why it's called a whole and not a vertical asymptote. In the second one, if we were to factor the top, we would have x plus 3 times x plus 1. And the denominator would have x plus 4 and x minus 4, if you were to factor that. Now, I see absolutely nothing in common. There is no x plus 3 down here, no x plus 4, no nothing. So therefore, you take the denominator that's left and you set it equal to 0. So you'll get x equals negative 4 and you'll get x equals a positive 4. Those are called vertical asymptotes because you could not remove them. They are in the final denominator of your equation. They could not be factored out and canceled or reduced with anything in the numerator, which means they become vertical asymptotes. If you can remove something that becomes undefined, it's just a whole because you were able to remove it. If you could not cancel and remove it, it becomes a vertical asymptote. So now to recap, I would like for you to pause the video, attempt to do these two problems, and then resume to see your answers. So in the first one, the top part is going to be x minus 9, and the bottom part can factor into x minus 2, x plus 2. I notice that there's nothing that cancels, so I'm going to take my denominator and I'm going to set it equal to 0. So therefore, I'm going to get x equals 2 and x equals negative 2. That is going to be my points of discontinuity. Now I got to decide, is that a whole or is that a vertical asymptote? A whole is when it had gotten canceled. Neither of these got canceled, so therefore these are both vertical asymptotes. Now this next one, in the top I see that I can factor out a 2 and I'm left with x plus 5. In the bottom will factor into x plus 5 and x plus 3. Now I do notice that something does cancel. And when it does, I am left with the equation 2 divided by x plus 3. That becomes what the equation or what the graph will eventually look like. It will look like this, not the original. So we got to figure out what happens. So we have two things going on. We have an x plus 5 that's in the denominator, the original denominator, that got to set equal to 0. So I'll get negative 5. And I also have an x plus 3 in the original denominator, and I got to set equal to 0. Here's the deal. One of these is a whole, one of these is a vertical asymptote. The x minus 5 is what had gotten canceled, meaning that was a whole because you were able to remove that undefined part. The x minus 3 is still left in the denominator, so therefore the x equals negative 3 is going to be considered, I'm going to just write VA for vertical asymptote. Again, if you were able to remove an expression, then that becomes a whole. That's why x plus 5 is a whole. Whatever is left over that was not able to be removed, that becomes a vertical asymptote.